So good afternoon, everyone. Welcome back to the lecture of control theory. So today we'll begin with the introduction to digital control. First, let me review a little bit about continuous control system. You can see here a block diagram of a continuous control system. First, you have planned. You need to do the mathematical modeling when you need to do a simulation. So you have a dynamic equation in the form of differential equation represented by this block. And for this plan, you inject some input, then you get an output. And if you want to control, you need to measure the output by a certain sensor. So you compare the signal from the sensor with the reference. The reference here is the desired. So you can calculate the error between the desired and the actual one, the desired output and the actual output. So from the error, the controller calculated and then inject some input to the plan. So in here you can do the simulation using certain numerical method. Okay. For example, if this plan is a DC motor, then the input is voltage and the output can be angular velocity or angle. Okay. So you have all the mathematical modeling and formulation for controller. Then you can do a simulation using some numerical method. For implementation, you can make a subtractor for this part, just for this part, and you can build a circuit to make a subtraction, okay, to get the error, and you can also create a circuit that represent a controller, a type of controller, for example, proportional integral controller. And for sensor, you can also have certain circuit, for example, a tachometer that can measure speed. So when it is rotated, the speed, when this one is rotated, then there's it generate signal, but it's a form of wave, sine wave, and then you can do some rectification in order to get the constant, in order to get the DC signal. So in here, to control a system, for example, a DC motor, you need to have this kind of circuits, right? If you can select all the components correctly, then you can implement it and you can get good result. But not always, especially during the design of controller. Perhaps you need to do like trial and error method. Then you may select some component which are not correct. Then what happened? You need to redesign. You need to modify your circuit, right? After you implement it and you get a not good result, then you redesign. You need to change the components. So the iteration process takes time, right? If you use the control method as analog, it's called analog. Okay, you deal with your controller, your subtractor, comparator, or everything is built based on electrical component. So the iteration process is not convenient. It takes time. That's why digital controller was introduced. So what is the advantage of this type of controller? So it increases flexibility of the control programs and decision making or logic capability of digital control systems. So let's say you can have a general purpose circuit or microcontroller or computer. Then when you change the formulation of controller, you just need to change the program. So the iteration process does not take so much time, right? With that, we just need general purpose to some extent, okay, general purpose device, components, or computer or microcontroller, right? So here, so where digital things take place? Well, this is planned, even though it can be modeled in the form of differential equations. When you implement, it is actually the real hardware, the real physics, okay, physical phenomenon of the system itself. So the controller that you need to compute only this part, okay. So this one is hardware or the system itself, okay, system itself. This one is sensor, also a device. What you need to compute, you need to calculate based on the formulation of controller, based on the reference or desired output, the data from the sensor of the actual output, and the formulation of controller, right? Oh, sorry, maybe around only this part. Yeah, around here. Yeah, many cases digital to analog converter is outside. Look, in some case the computers only take this part, but in some case, like for example microcontroller, the digital to analog converter is also included within it, okay. That's why you can see this block like that. So yeah, actually when you program this part also inside here, but here maybe just missing this part, okay, because you can easily calculate the difference between the reference and the actual output. Yeah, reference can be called desired output, okay. So I shoot at a photo of microcontroller, for example, like Arduino, where I can quickly find it. Microcontroller for you, like Arduino. Yep. Oops. Image. Yeah, so this is type of a microcontroller that you can be programmed to calculate the error and calculate the input that needed to be injected to the system. Okay. Yeah, so this one is just another representation. So you have microcontroller, you have set point. So this one equivalent to the set point actually. Set point, and then you have got the actual. You have subtraction in here, and then you have controller formulation in here. Okay, so basically these two are just the same thing, right? Okay. So here the key term of digital is that when you calculate, you need to calculate the amount of input needed to inject to the plant. You just take samples, okay? Samples from sensor data, sample from desired output, and then you compute it. Okay, the microcontroller need to compute it. So in that case, let me introduce the term samples. So I should have, here. Let me take up here. Okay. So what device that do the sample task? Let's say if you have continuous signals like this, then let's say the simple case, the signal is just a voltage from battery. So let's say it can be just straight, but if you need to sample data at different time, you need a device to do that. Okay, or let's say you have power source that you can change the voltage, so voltage can go up and down, but then you need a device that pick up the value of data at the respective time. Okay, let's say every 1 millisecond, let's say this period is 1 millisecond, just example. So every 1 millisecond you pick up value from the signal like that. That's called sampling. And the device that do the job is called analog to digital converter. Okay, you have analog signal, then you sample it, you get sample data like this. Okay, and then you also need, look at here. Okay, so sample is obtained from sensor, analog to digital converter. You get sample into the controller to compute. But then your plant is continuous system. You need to give the input as a continuous. So when you give sample of input, okay, you just give sample, you update the value every sample time. 1 millisecond you update one value. 1 millisecond after you update another value. But this device will hold the value in some way, hold the value to be continuous, and then it inject to the plant, right? And this device is called digital to analog converter. Okay, so digital means this samplings, you calculate based on sampling data. Analog means continuous data, continuous signal, to be precise. And let me introduce a term so-called zero order whole. Let's say the value computed from microcontroller at this level, when it's sent to digital to analog converter, this one, it need to hold for a period of sampling time before it receive the new value. Okay, and if the whole value is constant like this, then you call it zero order whole. Okay, zero order whole. Okay, now let's practice. Just warm up to get familiar with samplings. Okay, so read this and try to understand the question and answer. Let me read for you. Suppose a radar search antenna at the San Francisco airport rotates at 6 revolutions per minute. So 1 minute it can complete 6 circles. Okay? And data points corresponding to the position of flight 1081 are plotted on the controller screen once per antenna revolutions. So the antenna rotates once revolution and it record the data of one aircraft. This one, okay? Flight 1081 is traveling directly toward the airport at 540 miles per hour. A feedback control system is established through the controller who gives course correction to the pilot. He wishes to do so each 9 miles of travel of the aircraft. And his instructions consist of course heading in integral degree values. Then question A. What is the sampling rate in seconds of the range signal plotted on the radar screen? Okay.
0.1.
Sorry?
0.1.
0.1.
Sampling per second.
How can you calculate?
Because there is a 6 revolution per minute.
Yeah.
So that's one revolution every 10 seconds.
Yeah.
So that's one sampling every 10 seconds. So 0.1 sampling per second. I don't know.
So okay, so 6 revolution per minute, which means 6 points, 6 data points every 60 seconds, right? So to find the sample time, you need to calculate the period from one point to another. So how many seconds?
10 seconds.
Yeah, 10 seconds actually. Sample time is 10 seconds, right? So sampling rate is 10 seconds. What is the sampling rate in second of the controller's instructions? So you know that the flight is traveling at the speed of 540 miles per hour. Okay? And feedback control system is established through the controller who gives course correction to the pilot. He wishes to do so each 9 miles of travel of the aircraft. So it means every 9 miles he needs to send a signal back to aircraft to correct the heading. Okay. So what is the sample rates? We know that the speed of the aircraft is this one, 540 miles per hour, and every 9 miles we want to send a data, a set of data. So 9 miles. So you can calculate the duration every 9 miles, right? So uh, duration every 9 mile equal to 9 over 540. So equal to what? 1 over 60. 1 over 60, this is hour, right? So it is 1 minute, right? So it means it's 60 seconds. So every 60 seconds, the radar station send the signal to the aircraft to correct the heading. Okay, so this is 60 seconds. Identify the following signals as continuous, discrete, or digital. Okay, the aircraft range from the airport. So this one is continuous, discrete, or digital.
It's discrete
Why?
because it's not changing.
Aircraft range.
Maybe it's continuous because the radar spotted one time.
Yeah, it's continuous, but it's not in that sense. It's continuous if we assume that the speed is continuous. So at any time you select, you can calculate the range, right?
Okay.
So it is considered as continuous. The range data is plotted on the radar screen. So this one is discrete or continuous. Yeah, because the task of the radar station is to record the data every one round, right?
So it's discrete.
So it's discrete. Yes.
What's the difference between discrete and digital?
Digital here. Yeah, digital here means just binary,
Okay.
because discrete actually is in some sense also digital, right? Okay, this one, the controller's instruction to the pilot.
Discrete because it's every 9 mile and everything.
Yes, every 60 seconds, controller instruction is sending feedback, right? And the pilot's action on the aircraft control surface. Is it continuous, discrete, or digital?
Continuous because no one is trying to control it.
Because he's going to take action when he got the information from the controller instruction, whether he need to turn right or left,
Okay.
right? So just right and left actually.
So it's discrete.
Even more specific than that, because he action only two.
Yeah.
Oh, so
it's digital.
digital, yes, it's just binary. And question D, is this a continuous sample data or digital control system?
Sample the data.
Sample data. Does it include control?
Well, we asked the pilot to.
Yeah, because you got the feedback from the radar station to the pilot to correct the action, right? So it's a feedback control. So it's supposed to be a digital control system. And the last one, why also the so that it is possible for the pilot of flight 1081 to fly a zigzag course which would show up as a straight line on the controller screen. Okay, just answer this question first. So this means okay, let's say you have a radar that can it's just spin every 10 seconds, right? 10 seconds complete one revolution. Let's say this is radar, so this should be just something like this, okay? And the aircraft fly like this, okay? So the zigzag motion means it may fly like this, and then like this, and then like this, okay? Maybe several points like this, several points like this, okay? So so let's say this is radar that scan, and also it's also display in the screen itself. Let's say the screen is okay. Let's consider this one a screen as well. No, wait. Yeah, let me draw the screen only. So the question asks you to show that this airplane can fly in a zigzag path, but the display on the radar is just straight line like this. Is it possible?
Yes.
Why?
If the frequency of the radar match the period of the zigzag,
Yes.
it will always appear on the same.
Yeah.
The same
So it means when aircraft appear at this point and this point, okay, right? I think the way I draw is not so good, I guess. Let me draw again. The parts. So let's say so when it's here and then it's here and then it's here, the radar would register it as a straight line. Yeah. So your answer is that if the zigzag has the same frequency as the frequency of sampling data of the radar, right? Yeah, that is correct. And now the next question is, what is the lowest frequency of a sinusoidal zigzag course which will be hidden from the controller's radar? Yeah, so actually you just said the frequency, but it can be like the frequency is higher like this also, right? Also make the registration in the radar as a straight line, right? But then the question asks you to find the lowest frequency, which means can be this one represented by this red one. So now what you know is that along each line, the aircraft has the speed of 540 miles per hour, right? And every 9 miles, no, every 10 seconds, the range of the aircraft is registered on the radar screen. Okay? Every 10 seconds, right? So this one I would say is okay in seconds. Oh, one more zero. So what is the frequency that the lowest frequency when it come here to back there and then come back here? Or it's like this. This is just half frequency, right? This just half frequency. So this one is in some sense. When it fly along this path and then it just come back like this, the radar register it, right? So what is the frequency of this one? So now you have 10 seconds here and 10 seconds here, right? So what is the lowest frequency?
20 seconds or 120?
Yes, it's so but when you express the frequency, so the total period should be, this is period? No, this is not period, right? This is not period. This is a half period.
Yes.
So actually the total period is 40.
Well, to me, half the period should be 10 seconds.
Half period is.
Why half period?
Wait. From here to here is 10 seconds, right? Right. That's right. Okay. So half period is 10 seconds. Yeah. So full period 20 seconds. So what is the frequency? Over t, right? So it's equal to 0.05 hertz. Okay, so I mean you understand the terms sampling and frequency or something like that. Then let's move to the next problem. If a signal varies between 0 and 10 volts, and it is required that the signal must be represented in the digital computer to the nearest 5 millivolts. That if the resolution must be 5 millivolts, determine how many bits the analog to digital converter must have. Okay, try to calculate. So resolution is 5 millivolts. You have the whole range as 10 volts. Okay, so it's something like this. How do I? From 0 to 10 volt, you quantify resolution as 5 millivolts. Okay, so from one value to another 5 millivolts. Okay, so how say So from the range from 0 to 10, how many number of 5 millivolts? You understand the point?
Yeah.
So you take 5 millivolt times what number to be 10? Okay. So it means N times 5 millivolts equal to 10 volts. So you find N first. What is value of N? N equal to 10 divided by 5 times 10 to the minus 3. So you have 10 divided by 5 is 2. So you have 2000, right? And it's 2000. So how many digits of binary, how many, what is it called? How many bits? How many bits you need to have in order to have different like 2000 number? Let me just give you example. You have only 2 bits. Okay, if 2 bits, you have 0 0 0 1 1 0 and 1 1. So you have only one. Okay, 0 1 2 3. It means you have only 4 number different, right? In this case, N equal to 4 only. So to get 2000, how many bits?
11.
11.
But usually it's an even number, so maybe 12.
Yes. So actually N equal to 2 power N, right? Or maybe we can say this N should be less than or equal to 2 power N. This is number of bit, okay? This one. N is number of bit. So N can be like 11 or 12, right? So it depends on how convenient you make it, whether 11 bits or 12 bits. Okay, so I add another question. Let's say if I only have 8 bits, like I don't know, operate at 8 bits. So what is the resolution if you want to quantify the range from 0 to 10 volts? Now just give only 8 bits. Li Hua, you calculate only 8 bits, then what is the resolution?
It's 10 divided by 2 to the power 8.
Yeah. So the resolution would be 10 over 2 to the 8. Okay, so the next problem. Use MATLAB or Scilab and make 2 plots of y versus x for x equal to 1 to 10, and put a plot of y equal to x square on top of the page and y equal to square root of x on the bottom. It means you plot using subplot. So you have this one is the plot of, okay, this one is a, this one is y, and this one is y equal to x square, and this one is y equal to square root of h. Okay, so now you can use your computer. Okay, so I'm not going to show you now, you try first. You don't have